YouTube, once again, I'm revisiting this topic, the power triangle. Once again, one more and last time. This is a self note for myself. So if you guys want to join me and go along, you're welcome to watch. If not, go ahead and skip this video. So here's what I'm trying to figure out here. So the power triangle, and what I'm trying to do here is put a kind of like a cheat sheet for myself so that I can understand uh, have like a more of a short memory or a long-term memory concept so that by the time I take that exam, I know exactly what I'm dealing with. One of the subjects is the induction motors or synchronous machine, and this is what this topic really covers. Has always been my situation where I struggled the most. So I'm trying to put something together, and please let me know if you disagree with any of these statements. Go ahead and add a comment so that I know better or the audience will know better. But here's what I came up with, and you let me know if you agree or disagree. So the idea is what I draw here is basically think of this as the positive axis. This is the negative axis. So in this case, power is going to be the same regardless. But what really changes is your apparent power versus your reactance power. So what I did here, and one thing I kind of forgot to do, is your theta is measured by theta V minus theta I. What this really means, which we always reference of the voltage at 0 degrees, is that when given a power factor at, let's say, 0.8 and it's lagging, let's just go ahead and solve to find the angle for this concept. It would be theta cosine inverse of the power factor, and that gives us, we got 36.86, but for this purpose of this video, I'm just going to go ahead and round it up. So let's just say 37 degrees. Because it's lagging, I know that for my current, given current, so let's say that our current is 20 amps, then I know because the power factor is lagging, my actual complex current is 20 amps, negative 37. But what does that mean for my S? And let's say S somehow was solved, and let's say it's 100 kVA. All that it really means is that my S would be the voltage, the angle of the voltage minus the angle of the current. So in this case, it would be 0 degrees minus negative 37. You could see that this comes out to be 37 degrees. So your S would be 100 kVA angle 37. Just be mindful of that, because one of the biggest mistake, myself included, that every time I see the word lagging, I assume that the angle is negative. In this case, for the current it is, but for the apparent power, it's positive. So just be careful with that, because that goes back down to the concept. Oh, I apologize here. Let me see if I can actually update this text. This actually should say leading. Okay. All right. So for a leading power factor, you can see for some reason the kVAR is negative, which is correct because our S will become negative. But let's take a look at it once again. So going back into here, so we assume that we have a power factor that it's leading, and we said that the degree is 37 degrees. Because it's leading, for the current, it's going to be positive. So our current is going to be 37 degrees. And our S is going to be negative 37 degrees. And the reason for that is because the angle for S, or just theta, is theta V minus theta I. So if we take a look at this, 0 degrees minus 37, you get negative 37. So this whole diagram here is really just more of a reminder for myself to know that when a power factor is lagging, then this synchronous machine is considered as an inductive machine, which is consuming the VAR, and it's positive, which in a way is classified as a motor. And a motor, in this concept, your internal voltage, which is the EO, is less than E. So meaning your terminal voltage, or E, is actually giving out that power to EO. And this is the direction that it's going. Now, when a power factor is leading, then the power triangle, or the synchronous machine, is considered as capacitive, which is supplying the VAR. And this is the direction that it's going, which was also classified as a generator, meaning our internal voltage is greater than the terminal voltage. Okay? Now, having said that, we're going to kind of go and explain in more details regarding the phasor diagrams. This is another area that I struggled with in the beginning, and now I'm trying to really put it all together. This phasor diagram, once you understand it, it really will help you out in the long run, because you can put things together. What I wanted to show you is this first three options here for the phasor diagrams is your motor. And how do you know it is an actual motor versus a generator? Is because your EO, your internal voltage, lags. Once again, I gotta fix my typo, I apologize. Lags E, which is your terminal voltage. So if you take a look, you could see that the EO in this direction, you can see EO is at the negative, so that means it's lagging the terminal voltage. Same concept, it's lagging terminal voltage, and it's also lagging the terminal voltage. It's in the negative side. For a generator, your EO leads the terminal voltage. So there you go. If you look at it from the negative positive coordinates, E is leading the terminal voltage, EO internal voltage leading the terminal voltage, and the same concept here. The only thing you want to be mindful of now, looking into this phasor diagrams, by looking into this, now you need to measure the real value of the internal voltage to the magnitude of the terminal voltage. To measure the volume of it, that's going to dictate if your system is overexcited versus underexcited. So for example, this phasor diagram here is a motor. Now our question that we need to ask ourselves is this motor overexcited or underexcited? And the best way to know that is basically you need to find the real value of your internal voltage. In this case, it would be the horizontal. So let me see if I can, I'll just go ahead and put it in orange. So if you make this as like a right triangle, and this is your real value for EO. It's going to do that. Then you could see here, the real value of EO is less than the magnitude of E. That is what makes this as underexcited. So I'm just going to put UE. Okay? If you take a look at the generator side, regardless of EO leading or lagging, for an underexcited, for a generator, your EO, same concept here. If you draw the real magnitude or the real value, compare it to the terminal voltage, you could see that EO is less than E. This is considered as underexcited. Okay? So Going back to this section right here, we know that this is a motor and this is a generator, but is it considered as underexcited versus overexcited? Well, in this case, you could see that the actual real magnitude, or the real value of EO, internal voltage, is equal. So let me just do this so that we can just for comparison purposes so that you can see, and this is going to help me out a lot. You could see here our real terminal voltage equals E. This is considered as a unity, so your power factor is considered as 1, and in that situation it's considered as ideal. So it's not underexcited and it's not overexcited. So let me just go ahead and do the same thing here. Okay. And we'll walk through the current after this. Maybe I should have discussed the current before we did this, but this is going to help us out regardless. So this is a unity. This one right here is underexcited. I think you can guess by elimination over here that this is going to be overexcited. But why is it overexcited? Well, once again, if you compare the real value of your internal voltage versus the magnitude of your terminal voltage, you could see in this case our EO is actually larger than E, and this is what makes this overexcited. Same thing here. You could see that our EO real value is larger than E, and that also makes it overexcited for the generator. Now going back into the power factor, I think we solved the power factor here where we said this power factor is technically 1. This is an ideal system. What will make the other two? Well, for a motor, it's an interesting concept. If you take a look at here, you could see that I is lagging. So in this case here, you have a power factor that's lagging. For a generator, the power factor is leading. Okay? If you take a look here, when the motor is overexcited, the power factor is leading. And if you take a look at the generator, when it's overexcited, the power factor is equal to it's lagging. The takeaway here is just I need you to know that when it's overexcited, right, when it's an overexcited system, then it's supplying. I guess I could just write this down here. I'll put it in white. So when it's over and the system is overexcited, regardless if it's a motor or it's a generator, then it's considered as supplying Q, which means Q is less than 0. And when it's underexcited, it's basically consuming Q, which means Q is greater than 0 VAR. And this is for a synchronous machine. So I think this is really important to remember and just be mindful of, that when it's overexcited, it's technically the machine is supplying a reactant, and your Q is considered less than 0 VAR. And then when it's underexcited, it's consuming, and Q is in the positive side. Very independent of one another, but it's just nice to understand the power triangle in reference to inductive versus capacitive, informing the relationship from internal versus external. Here is basically, be mindful that it's not that it's lagging versus leading. This is really more of just saying that if you take a look here, you're looking at an internal voltage equals EX plus E. Here you're looking at, oh, sorry, man, I apologize. This is, hope it does not mess up anybody. I had it the opposite way. What I meant to say here is E, terminal voltage, actually equals the summation of EO plus E of X. Take a look at your EX, and here's your EO. And then here, your terminal, or your internal voltage, equals E plus EX. Okay? That's really what that means. And if you go down here, just keep in mind that when you think of a motor, your internal voltage lags the terminal voltage. When you think of a generator, your internal voltage leads the terminal voltage. Now, depending on the magnitude and the real value of your internal voltage compared to the terminal voltage, then that's when you can classify each system if they're underexcited or overexcited. And based on what system it is, motor versus generator, you know that if the generator is underexcited, then the power factor is leading. But you'll also know that if a motor is underexcited, then the power factor is lagging, the opposite of each other. I think the best way to remember this, how I remember it, is I reference the motor, and knowing that whatever the motor acts as, the generator is completely the opposite. So the way I look at it is, when the power factor is lagging, I know that the motor is underexcited. So I automatically know that the generator must be opposite. When the power factor is lagging for a generator, then it's not underexcited, it's actually overexcited. Do you see the comparison? Same thing here. I know that for a motor, when the power factor is leading, then the motor is overexcited. So for a generator, I know that when the power factor is leading, it's going to be underexcited. So that's the way I can actually relate to those two relationships, that they're completely opposite of each other. That's really all I wanted to bring out. And what I'll do is I'll leave you with a short diagram that I drew once again, that I think is going to help you out a lot. But what I'll do in this case, I'm just going to cross-reference it in quadrants. So let's do this. And this is going to help you out. Okay, so power factor, let's call this what? Power factor lagging. Okay, and this is going to be for a motor. And power factor leading. And then this is going to be for a generator. And we're going to do the same thing. Power factor leading. And power factor lagging. Okay, so for a motor, we did discuss that when a power factor is lagging for a motor, then it is considered as underexcited. We know because the power factor is lagging for a motor, it's underexcited, then the generator is going to be overexcited. Same thing here for a motor. When a power factor is leading, then it's overexcited. I know now that it's going to be the opposite for a generator. It's going to be underexcited. I hope that you guys can see the difference or the comparison. Power factor lagging for the motor, power factor is leading for the generator when they're underexcited, and vice versa. Power factor leading for a motor, power factor is lagging for a generator when it's overexcited. I hope this helps you guys out. This has been helping me out a lot. Best of luck for everyone who's going to take the exam, and for those that already passed, congratulations. I can't wait to get to that level. You guys have a good one, and take care.